Okay, evidently we had some technical difficulties with the computer here, so hopefully if someone can hear this, if you would send me just a real chat message and we can get started here. Okay, all right, thank you, Hans. So what we're going to accomplish here today is by the end of this seminar, you'll be able to identify the key considerations when you're selecting a lens for your digital camera, be able to tell why lens resolution is important particularly for inspection applications, describe the important lens specification factors, and then also perform some quick calculations, some kind of napkin calculation factors for your digital camera. I've got those here. And select the most appropriate lens, which is what we're trying to do for your application. So why is it so important today? Remember, the early machine vision systems, they were big and costly. They were low resolution. And that fledgling machine vision industry relied on cameras and lenses that were developed for closed-circuit television. There wasn't anything else. So the RS-170 standard in use at the time, that specified 525 lines in a tube. So when we started to see digital cameras, the first one, of course, that came out was VGA. It was almost 525 lines. It was 640 by 480. And so CCTV lenses were still adequate for these early digital cameras. But what we have seen in recent years is the introduction of megapixel cameras and their sensors. So machine vision application engineers have begun to see the limitations of these CCTV types of lenses. And I say machine vision, again, machine vision applications are migrating from the factory floor. We'll talk about this a little bit later, but we have traffic, we have agriculture, we have all of these other applications that are using machine vision techniques outside of the traditional machine vision environment. So, but today's cameras require quality optics, and the pixels are smaller, the formats are larger. And so we need to take a look at the appropriate lens for them. The comments of a machine vision, I've changed the slide. Used to have a part there, but now I have seen. It's been used, machine vision has been used for decades to describe an image processing environment where a computer makes the decision based on the execution of some software algorithms rather than a human inspector. Now, needs to increase speed and repeatability and objectivity. Machine vision algorithms have historically been restricted to the factory floor. As these machines, as I said earlier, the machines have become more powerful, so we're seeing a migration of these automated inspection methodologies from the plant floor to other environments. So the illustration has the components of such a system, whether it's indoors or out, have some kind of a scene or a part, something that's illuminating that, whether it's ambient light or some controlled light source. That light then is reflected by the features within the scene, and it's transmitted through a lens. Typically, though not always, larger than the image sensor, means that the light is being bent or refracted through the lens to be detected by the image sensor. And in this process, we're going to see some distortion. Another topic for another webinar, maybe on telecentric lenses. The image sensor is an array of photosensitive elements that detects the intensity of the light or count the number of photons that impinge upon that element at any given time. Light then is transmitted into an electrical signal for interpretation by a computer. The processing algorithms are used in a variety of imaging products. So the question that we ask in machine vision is, who makes the decision. If a person is making some sort of a determination based upon the image data, for example, is that Joe or Joanne, then that powerful processor with color, stereo, and depth perception called the human brain, that can fill in some of the blanks that might be missing from the picture. And we see this, we do this all the time. We're always filling in the blanks. On the other hand, if a computer is expected to make a decision based upon the features in the scene, then they're still not that smart. Information must be pure. So the modern SLR cameras, the cell phones, security cameras, that kind of thing, they've got some pre-processing algorithms that alter the data for color, brightness, contrast, other factors. But on inspection applications, by definition, require pristine information. Factors to consider when we're looking at the object or the scene. Is the object, is the location, is it controlled or not, moving? There are a variety of factors to be considered. Now, if not in a repeatable location, we may need to use some location software. Also, that might affect how the light is reflected off the object. And notice that cylinder, the pill bottle in the upper left-hand corner. If the cylinder moves, the light is coming from the right-hand side right now, and they're trying to read the barcode. If that cylinder moves, that light level there is going to be different. So, likewise, in the parking lot picture, when it's daytime, the light is going to be different. So, illumination is one of those factors to consider. Whether the object is moving, the size. You can see here we have a number of different. One we're looking at a parking lot, another one we're looking at a very small park. So, but directly below are the attributes that directly affect the lens attributes. So the size of the object, the field of view, the size of the defect that we're trying to find, or the size of the attribute that we're trying to extract, and also the working distance. These are the factors that we're going to use when we're considering our lens. Now, a little bit about illumination and how change can affect that, but also the wavelength. Is it visible light? Is it IR? The brightness and intensity. If you're looking at a stadium, for example, and you're trying to do maybe a population count or something like that, as the sun passes over that stadium, the light is going to be different, and so that's a challenge. If looking at some hyperspectral, so for example, the middle picture, we're looking at various conditions on the human body. They'll use dyes that fluoresce at different wavelengths so that they can extract different views as the doctor is in there working. Then that's going to be a consideration for the lens. Because, for example, silicon is transparent to IR. So you need to have a special IR lens in order to bend that light or reflect that light through the lens. So the brightness and intensity, and believe it or not, in that down in the lower left-hand corner, actually a way to light a high-velocity projectile, the wavefront in the air of a high-velocity projectile. So that's going to be a consideration when you select your lens. On the left-hand side, they are ambient light, and then on the right-hand side, they're controlled lighting. So that's going to be a factor. You color your wavelength, again, the ones in yellow, color and wavelength, bright intensity, and your image contrast. The image contrast is going to be critical. Considering our camera, the camera is the other half of the optical delivery system. It captures light from the scene or the object and then transforms that light into electrical signals for interpretation by the computer. So when you select the camera, data throughput may be a factor. If you have a high-speed application, you may be considering that. that will determine the kind of output that you use. Under certain conditions, the frequency response of the sensor chip may also be a factor. And if the object is moving, then you want to use a global shutter rather than a rolling shutter. So this digital transformation of light into electrical information is an image sensor and the supporting electronics. The image sensor is an array of sensitive elements or pixels, and an individual pixel can vary in size from a micron to several microns, and they're usually square nowadays. Each pixel is the amount of light that impinges upon it over a given period of time. You might think of it as a photon bucket. You know, we have big pixels that are big buckets, and they can capture lots of photons over time, and smaller pixels are small buckets, and they can't capture as many. So the photons per atom yields the intensity of the light at any given time. So color cameras, every pixel looks at intensity. Color cameras simply put a color filter over the sensor so that they respond to certain colors. The principle is still the same. The size of the sensor array determines the optical format and to some degree the resolution. The optical format is the image sensor size. Many lens manufacturers will describe their lenses as megapixel, but we'll in a few minutes, it's the size of the pixel within the matrix, not the number of pixels in the matrix, that really determine the lens resolution. Lens is the other half of the optical delivery system. Many factors are important for the optics. We could look at the type of camera, the type of mount, whether global, rolling, that kind of thing. Directly affecting the lens, again, are the ones in yellow. Whether it's a line scan, area scan, or embedded system, that's going to be a different size of lens, mechanical size. Where sensor array is a VGA or a megapixel, the format and the size of the pixels, those are all factors that we'll take a look at in selecting our lens. So, optics, these are the factors now. Remember, we looked at the scene, we looked at the lighting, we looked at the camera, now we're at the lens. The defect or the attribute, the size of the pixels, and the sensor array, those are all going to be in our resolution factor. Whether it's a line scan, area scan, or embedded, that's going to be usually the size of the lens, the working distance, going to the focal length, and also to some degree the field of view. And the brightness is going to be the F number, and whether we're going to select a visible light, an IR, or some special type of lens. So these are all the factors that we consider when looking at selecting our lens. So the question is, where do we start? I don't know if any of you saw the 1984 movie Dune of Frank Herbert's Dune. I'm a sci-fi fan, and Princess Erlin says, a beginning is time for taking the most delicate care balances are correct. Nothing can be said then for machine vision. If anybody has looked at this, there's so many variables that you need to look at in order to be successful with a machine vision application. So basically, I just say, begin at the beginning and find what is the application problem. What are we trying to do? And it could be any number of things. And again, what we've seen is, we've started, we've got ID code readers, and we have gauging, and we have part identification. We have industrial robot guidance. As we start to migrate off the factory floor into the environment, those problems become even more complex than they are when you've got a fixed part, part of the position with fixed control lighting and that kind of thing. So it's a real challenge, even more challenging than it has been in the past. We're going to assume for this discussion that all of that stuff has been taken care of, and we're just going to use a systematic approach after we've taken a look at our application. So to select the lens now, all attributes notwithstanding, the first is to determine the mechanical properties of the lens. So what type of mount, the wavelength of your light source, that kind of thing. Determine the application resolution requirements are. So you know what your size of your defect is, and you need to extrapolate from there. Calculate the required camera resolution. So then, yellow, those are the steps that we're going to go through to select our lens, and through these step by step. Step is to determine system accuracy. System accuracy is going to drive what the camera resolution is. If you, for the sake of our example here, let's just say we want to detect a 0.1 millimeter feature on a surface that's 75 millimeters square. And assuming, see here in yellow, we're assuming the appropriate lighting and high quality optics is the required camera resolution. So for camera resolution. And then for camera resolution, pixels equals field of view over accuracy over 2. And the reason that we say 2 is if you look at the right-hand image, basically that is the part, and that's the pixel matrix with some grayscale values superimposed over the part. Now, the system cannot detect a transition from light to dark or a lighter to darker in only one pixel. So you need 2 to detect a change. That's why your feature should span 2 pixels. So for the sake of our example then, our pixel must cover 0.5 millimeters. And again, we usually don't have the object is going to be within the field of view of the camera. So if we have a 75 millimeter object, we're going to have a 100 millimeter field of view, let's say. So then over 100 millimeters, we have to have 2,000 pixels doing the math. Anyway, that's I have a spreadsheet, a collection of spreadsheets that have a number of these optical calculations. If you send me email, I'm happy to share it with you. So the next is to select the camera sensor. Now, you can look at the cameras. You may have already begun your camera selecting process when you, because of your lens, if it's a line scan camera, you know, you might use an F mount, or if it's an area scan or whatever, you're going to have a CS or a C mount lens. So you may have already gone down that road. And many camera manufacturers will beginning to specify the pixel size, and some even specify the sensor for they use in those particular cameras. So doing a research, I selected 2 sensors. One is from Anafocus and one's from Sony. And you see, well, let me back up. I forgot to mention that 2,000 pixels must be in the minor axis. So we need to be the most restricted. So you hear that these sensors, they're both megapixel cameras nominally, and they both have 2,000, at least 2,000 pixels in the minor axis, but no pixel size. So one has a 5 micron pixel size, and the other one has a 3.45 micron pixel size. And we can already see, I also have a chart of recommended series of lenses for pixel sizes that I'll be happy to share with you. Again, send an email. Recommended lens are 2 respective lenses, or the MP and the MPY series, which we'll get into later on. The important thing is, right now, we've got 2 5 megapixel cameras, one with 5 micron pixel, the other one with 3.45. And so, so somebody says, well, I want a 5 megapixel lens. Well, how do you know what your pixel size is? And we'll be discussing that. Before we get off the camera, just this was shared to me with me by Perry West, Vision Systems Design. I thought it was pretty good. If you're looking at cameras, smaller pixels, usually a less expensive camera. It's a smaller camera, which are going to need a better lens. And larger pixels are higher sensitivity, basically higher signal to noise with larger pixels than you have with the smaller pixels. And the reason, of course, is that, the larger pixels are able to collect more photons and have a certain amount of electrical background noise, so you have higher signal to noise there. And looking at the migration as we've gone from VGA through the megapixel cameras and now into multi-megapixel cameras, again, the Perry West, we see an illustration here of the pixel size. Because if they format, the format is about the same, pixels have to get smaller in order to fit into the same kind of an area, whether it's half an inch or 2/3 or whatever. So, into the topic then, we set our camera resolution and know that we're looking at 2,000 pixels, and we know that we have an option now between a 5 micron and a 3.45 micron pixel. So the lens is determined by a number of different characters. But we use this analogy as of the photon bucket. The smaller buckets have more detail at a light level. They have lower light, but more detail. And although there's a consideration here that the small bucket also means that the photons come in at a tighter angle. So basically tolerate less reaction than a larger pixel would. If you think about it, if I've got a big bucket, the photons can come in at more angles than it can with a small bucket. So these are specified in pairs per millimeter. That's resolution specification. That's the measurement that's performed at the factory, and it becomes a part of the lens specification. And the term line pairs per millimeter describes the ability to discern the edges, that is the border, between two lines. So you've got a white line and a black line, and they produce an image, and they basically look at how many line pairs can we detect before we start to have distortion. Trying to discriminate, we're trying to find an edge, discriminate between black and white lines. Now, this is going to depend a lot on intensity of the light, on the contrast. Basically, it is a measurement of contrast at a given line pairs per millimeter. The more line pairs per millimeter, the more contrast is required in order to detect the difference, or vice versa. The smaller the clearer they are, the better the lens has to be. Edmund Optics has a great explanation of this on their website, and I've got that information is on the resource page here later on. So what we were talking about with the angles and the sharpness of the pixels, small pixels, big pixels. We need more line pairs per millimeter with a smaller pixel. So let's calculate then the lens resolution. And this is the equation, but again, I have a handy-dandy sheet that I've used to do this. So we see for our example for the 5 micropixel, it's roughly 91 line pairs per millimeter is what we need to support that lens. The 3.45 micron pixel, we need about 145 line pairs per millimeter. So that range. So 90 and 145, depending on what type of sensors. You get this optical data is published by most manufacturers. Some write it on a website, some IP, but you can get it from everyone. When you're looking at the optical properties, and they'll send you what's called an MTF chart, and we'll get into it in a minute. We're going to look for about 30% contrast or better. And again, these lens manufacturers will make that information available if you ask for it. Here's a typical MTF graph, just to explain. Is a fairly complex topic. There's lots of good discussions that you can find on the web. Most of those that I've found relate to the study of optics, as a science and photography. You can sort of extract some of that that's relevant to machine vision. And there's a good one, again, listed by references. It's Wikipedia, MTF, and Edmund has another good discussion. But basically, this MTF chart depicts how contrast between the line pairs decreases as the distance between the lines decreases. And, it makes sense. You're not going to be able to discern if you're looking at, I think of it as a screen. You're not going to be able to, if the screen is really, really tight together, trying to just pick out the two, it has smaller than the screen size in order for you to be able to see it. But the critical factor when working with lens resolution. So here's an MTF chart, a typical MTF chart, and you'll notice that there are multiple lines, not the one, this where we have just lines, just as an example, multiple lines. And the reason is that the resolution of a lens is not linear like the array of pixels in the camera sensor. Those are manufactured, and it's just an array. It's kind of like, I use a screen analogy. It's just like looking at a screen. It's a bunch of little squares. But lenses are, their resolution can vary depending on where the light is coming through in the physical location of the lens. Typically, you'll find, and that's a function of the distortion that you have, or the as it's being refracted, as the light is being refracted to be focused on to that sensor. You have different. So typically, at the center, the lens is going to have the least distortion because it's along the mirror optical axis. The closer you get to the periphery, then you're going to start to see distortion. But again, it's not going to be linear. Some areas, if you go out from the diameter, you'll have, on one side, you might have a little bit of distortion. On the other side, you might have less or greater. So again, the point is it's not linear. And so you see the MTF chart, it shows you what the position, what the locations of those particular are, and then for your application, if you know that you're critical in a certain area, they can use that to your advantage. Now, again, a simple example of mod transfer function, and is a illustration of how it actually reads in the physical world to the chart. The upper lens, notice, has more clarity. And you're down to, you've got a spatial frequency of say 300 on lens, and you can have a contrast of 40% or so, 38%, and you can see by the curve down below that you get almost nothing. So, if the application is to detect a dot at a certain intensity, chances are you can use the lens on the bottom and you'll get acceptable performance. an object is to measure the diameter of a dot. Say you've got a solder dot inspection for an electronics application. We're trying to measure some features in an iris of an eye. So if you identify features or kind of things, you're going to need the it's the clearer is better, and that upper is clearer. So let's talk a little bit about and you send it through a lens, and then you put that onto some kind of a digital sensor. So usually a lens consists of a series of stages of light transmissive material, usually silicon, and the photons from the scene are refracted in various ways to be onto the image sensor. So time, of course, we're going to have some distortion, and oftentimes the purpose of the succeeding stage is to compensate for the distortion that was the preceding stage. So, again, multi-stage lens, some distortion, and quality really matters. Format. So the format refers to Vidicon tube terminology from the very beginning. Remember, we were using CCTV cameras, and they have nothing to do with the diagonal on the sensor, which is where your image circle is going to be. So they're listed here for convenience. Basically, that's the diagonal of the lens. So if you have, say, a 2/3 inch lens, you're going to be 11 millimeters diameter. You want to have a 11 millimeter image circle usually. Calculated, there's the calculation, the formula for optic format. They're usually listed, and the lens manufacturers will give you they'll tell you if it's for a 2-inch sensor or 1/3 or 1 inch or whatever. In this particular case, we looked up the cameras, and the camera manufacturers said, that one is a 2/3 inch lens, 2/3 inch optical format, and the other one is a 1 inch. So, now we'll look at for optical format for select lens. Important is because of the image circle, where the lens is a cylinder. So the center is a rectangle. So we're going to see projected onto our image, what we're actually going to see is in the left-hand column, we're not going to see everything. It's called vignetting. So we're not going to see the light that's outside that circle, that's outside the lens. So even though your sensor will transmit dark data, and you'll see it, monitor, and your inspection system will see it, there's no information there that the lens is transmitting. The right-hand column, the image circle corresponds to the format of the lens. You can see the opposite. The lens is fully populating the sensor, but remember what we said about distortion being at the periphery of the lens. So the right-hand illustration is going to yield better results because you're going to be more in the better the better part of the lens. Vignetting, and again, this occurs when you have a lens image circle that's smaller than your sensor. We calculate focal length, and again, there are equations for that. So and they're in the spreadsheet. So we found out for sensor format, we have a 2/3 inch lens. We have assumed a 300 millimeter distance to our object. So we've got some kind of machine constraints. This is where our application comes in. You make machine constraints or some kind of a real estate consideration in our application, so that we are going to be around 300 millimeters away from the object. We already know that our horizontal field of view is 100 millimeters. And so calculating, we know that we need, those are the focal lengths that we need. Now, no makes, that I know of, a 39.6 millimeter lens. So we're going to have, a 35 millimeter lens or a 50 millimeter lens for that, for the left hand, for the one sensor. Then you make a 25 millimeter lens for the 2/3 inch sensor. Calculation, so you do that calculation and then you can select from a standard lens size. And then with most vision applications, you just have to play with it a little bit. Let's put it together here. First, determine our application requirements. We determined that we needed 2,000 pixels for our camera. We have a field of view of 100 millimeters. Working distance of 300 millimeters. We know that our illumination is optimized for our application. We've taken care of all of the other mechanical and peripheral application considerations. So determine what the application requirements are, the application resolution, then determine the sensor resolution. And remember, it's the pixel size, not the array size. Then select our camera. And we had a sensor format of 1 inch or 4 inches, 1 inch or 2/3. And camera we came up with. So our lens, we know we're going to either need 90 or 145 lines per millimeter. And so we contact the manufacturer and say, we need to take a look at the MTF information so that I can know what I'm doing. And then calculated the focal length for a 1 inch, it's 35 millimeters. For a 2/3, it's going to be 25. And, down there listed some of the Computar part numbers for those respective lenses. Then now it becomes a matter of cost benefit. I've got 2 cameras. I may want to, depending on the application, if it's a light application, I may go with the larger pixels. If, then it becomes an application problem, what to do there. And also a cost benefit, because the higher resolution lenses are going to also have a higher cost. So it could be as much as 2x. But if you're, as during systems integration days, just from experience, many of you that have experience also, if you, it's a couple hundred dollars more